Welcome to AP Chemistry at Honeyniga High School. I'm Brian Brown, and today we'll be finishing Chapter 5, looking at the last two sections, different methods of calculating delta H's, Hess's law, and enthalpies of formation. Now, delta H is well known for many reactions, and it's inconvenient to measure delta H for every single reaction that could possibly occur or that we're interested in. However, we can estimate delta H's using published delta H values and the properties of enthalpy themselves. So there's a couple of different ways to go about doing this. One of them is by using Hess's law. Hess's law states that if a reaction is carried out in a series of steps, the delta H of the overall reaction will be equal to the sum of the enthalpy changes of the individual steps. So you'll notice over here on the left, we have two different ways of looking at the same general reaction system. In one step, we can go from here to here, or in two steps, we can go from there to there. Well, if this equals these two steps, then the sum of this reaction, or I should say, then that reaction should equal the sum of the individual steps that make it up. So that's fundamentally all we're doing with Hess's law is we're trying to look at how a series of reactions can equal a total reaction, and that must mean that the sum of their enthalpies must equal the total enthalpy. So because delta H is a state function, the total enthalpy change depends only upon the initial state of the reactants and the final state of the products. It's a state function. Concept of state coming up all over the place here. So here's how we're going to apply Hess's law. You're going to have some target reaction. In this case, it's 2 sulfur solid plus 3O2 gas yields 2 SO3 gas. Now, that's the reaction we're targeting. We want to find the delta H for that reaction. And we're given these two reactions. So that must mean there must be some way to mathematically manipulate these two equations to equal the top equation. And that's really our goal in a Hess's law problem, to try and get these two to add up to that equation, and then the sum of the enthalpies would equal the other equation. Now, up top is my target. So remember, I want to keep that in front of me. That's what I'm trying to get to. Now, I need two sulfurs on the left side. And if you notice, that first equation listed down here is the only one that's got sulfur in it. Now, conveniently, sulfur solid is on the left side. So that equation is written properly. It's got sulfur on the left. The problem is that is sulfur and it's only 1 mole of sulfur. Well, I need to know what 2 moles of sulfur is. So my target equation, I've got to get 2 moles of sulfur. So since we need to start with 2 moles of S, it looks like we should double that first equation. And if we double the first equation to get 2 moles of S, we also get 2 moles of O and 2 moles of SO2. And we also double the enthalpy change. Remember, enthalpy is an extensive property. It is dependent upon amount. So if we want twice the amount, we're going to get twice the energy involved. So if we rewrite that equation, doubling everything and doubling the enthalpy, we now have that. So that gives us our two S's on the left as a solid, just like we want. Now, since we need two SO3s on the right, that means where's our source of SO3? Looks like the bottom equation here is our source of SO3. Well, it's got two SO3s just like we want. The problem is they're on the reactant side. In our target equation, they need to be on the product side. So what do we need to do that bottom equation? That means we've got to flip it, and that's going to change the sign of delta H. So if we need to reverse that equation, we're going to flip the sign from positive to negative. So we carry that out for that reaction. Now I've rewritten it. What was a product is now the reactants. What was the reactant is now the product. And I changed the sign to a negative 198. Now notice we skipped oxygen. We only really worried about the sulfur and the sulfur trioxide. Well, the reason we skipped oxygen is oxygen's in multiple equations here. To try and balance the oxygen by manipulating the equations is going to be a pain. It's easier to balance the other things or to get the other things in the appropriate place and quantity, and then usually the oxygen will take care of itself. So at this particular point, if we add those two equations together, we do get the top equation. Well, if these two equations sum to this equation, that must mean these two enthalpies must sum to that enthalpy. And we end up with a value of negative 792 kilojoules. So if we have a reaction like this one we don't know the enthalpy of, we can use Hess's law to determine its enthalpy. And that's what I mean by we don't need to know the enthalpy of every reaction. We just need to know it for some reactions and know how to manipulate it. So that's Hess's law. The last section, 5.7, is dealing with formation enthalpies. And this is really another way to calculate enthalpies. And honestly, it's actually an application of Hess's law. It just doesn't look like it on the surface. But one of the things I'm going to try and show you is how this is really just an application of Hess's law. So, because Hess's law, the problem is, how do I know what equations I need to get? Well, in formation enthalpies, there's a cue to get all the equations you really need, and you don't even think of it as Hess's law, even though it really is. So another important method for calculating enthalpy changes is through the use of formation enthalpies. And remember, this is really just an application of Hess's law. Now, standard enthalpies of formation, which are written as delta H naught sub F, that's what you say for that little circle there. It's the change in enthalpy when 1 mole of a compound in its standard state is formed from its constituent elements in their standard states. Basically, you're forming a mole of a substance from the elements in the states they normally exist from. Now, the delta H of formation for free elements in their standard state is always going to be 0. It doesn't take any energy to form what already exists. So if you're trying to look up the formation enthalpy and it's an elemental substance, you're not going to find it in the table sometimes. That's because you're supposed to know it's 0 kilojoules. So free elements in their standard state doesn't take any energy to form them, so their formation enthalpy is going to be 0. Now, the little circle, what I call naught in this triangle, means we're measuring this under standard conditions, which would be 25 degrees Celsius and 1.00 ATMs. It's not something that's critical ever in this chapter, but that's all that little circle means. And that's going to pop up in a bunch of different chapters. So what is the standard formation enthalpy for SO3? Well, if you go to the back of your book in the appendix, you can see that if you look for SO3, you'll find in the back of the book that it doesn't list 2 moles of these, it lists 1 mole of these. So to get the formation enthalpy for this reaction for SO3, we've got to get it in the form of a formation enthalpy. Remember, it is formed from its constituent elements in their constituent states. Well, that's the state of sulfur and that's the state of oxygen, so that's good. But it's forming 1 mole of it. And in this reaction, right now we're forming 2 moles of SO3. So this energy is not our formation enthalpy. But to get it, all we really need to do is divide by 2. And remember, as an extensive property, if we have half as much, that means we cut the energy in half as well. So this would be what you see in the table for the formation enthalpy of SO3. And that's why it wasn't this original number, because that wasn't for forming 1 mole, it was forming 2 moles. These are standard formation enthalpies. They're molar formation enthalpies. It's the energy involved in forming 1 mole from its constituent elements in their standard states. Now, because calculating delta H from formation enthalpies is an application of Hess's law, we should be able to calculate the energy using either method, and we should, in essence, get the exact same thing in either case. So these are 2 different ways of doing the exact same thing. Now, we're going to calculate the enthalpy change for the following reaction using Hess's law, and then we're going to look at it from a formation enthalpy method. So here's the reaction in question. We are combusting C3H8. You're supposed to know this. Remember, meth, eth, this is propane, so we're burning propane. So this is basically what happens in your gas grill out on your deck. When you burn 1 mole of methane, you need 5 moles of oxygen. You're going to make 3 moles of CO2 and 4 moles of liquid water. And you also are going to have energy involved. We just don't at this point know what energy is involved. Now, if we look at this reaction as actually occurring in 3 steps, we have the propane breaking apart into graphite and hydrogen. And then we have graphite and oxygen reacting to make carbon dioxide. And if we have hydrogen and oxygen reacting to make water, we've got 3 reactions. And each of these reactions, reaction 1, 2, and 3, so here is the first energy of the first reaction. Here is the energy of the second reaction. And here is the energy of the third reaction. Well, our overall reaction can be expressed as the sum of these individual reactions. So we can use Hess's law to determine what this is going to be. So when we add these up, we end up with negative 2,220 kilojoules. So using Hess's law and the enthalpies of each of the reactions in Hess's law. So notice when we add these 3 together, we get 1 mole of propane. The two O2s and three O2s combined to give us five O2s. We've got three CO2s. We've got four H2Os. The hydrogens on each side, the four hydrogens on each side cancel out. So we really do have a reaction series that adds up to this reaction, and that must be the delta H of the first plus the delta H of the second plus the delta H of the third has to equal that delta H. And that's exactly what we're showing here. And that is found to be negative 200 or 2,220 kilojoules. So that's what it would look like as Hess's law. Now, let's calculate that same thing using formation enthalpies. The problem with Hess's law is, where do I get all of these equations and how do I know which ones to use? Formation enthalpies are much simpler. Now, here's the equation we're going to use, and it really is just an expression of Hess's law. The enthalpy change of a reaction, now this symbol right here you may remember from math class, is the sum of. So the number of moles of, or the sum of the number of moles times the delta H of formation of all the products minus the sum of the number of moles or the quantities of our reactants delta H's. So N and M are really stoichiometric coefficients. So we get those right from the balanced equation. So we really do need the balanced equation here because obviously as an extensive property, if we have more moles of oxygen being used or more moles of water being created, we need to account for that. So it's the sum of the enthalpies of the products times their mole amounts in the balanced equation, their coefficient, and then you do the same thing of the reactants and then you subtract. So what this looks like as a mathematical equation. Now, first I'm going to show you um, how this would look based upon the equation above. Now notice, it's products minus reactants. So I've got the products in red here. So I look up the formation enthalpy of CO2 in the appendix in the back of the book, and it says it's negative 393.5. And since there are three of them, I need to triple that. And then I do the same thing for the water. I find out what water is. It's negative 285.8 by the back of the book. And since there's four of them, I need to multiply that by 4. And then I add those two things together, so I sum them. So it's the sum of those two things. Those are my products. And I do the same thing on the reactant side. If I look up C3H8, I'm going to find that value. And since there is, in essence, one there, I only need one there. And since I've got 5 oxygens, and oxygen as a gas is 0 because elements in their elemental state are 0 for formation enthalpies, it's just 5 times 0, which is going to end up being 0. So I find out what my products are, I find out what my reactants are, I add them all up and then subtract them, and eventually I get essentially negative 2,220 kilojoules, just like I've got before. The reason it's slightly off is we have numbers with more significance here using the appendix in the back of the book. So in essence, this is equaling the exact same thing we did before. Now, that's kind of the book method. They make it look nice and pretty if I get rid of all this stuff and a nice mathematical expression for what's there. There's a simpler way to do this and a quicker way to do this, so I don't recommend using the pretty algebraic book method. I think the easiest way to do it is to just take a look at what you've got and write it right underneath each one. So the first one, C3H8, I looked that up in the back of the book, it's negative 103.85. Then I look up oxygen, it's 0. Then I look up CO2 and I look up H2O. Now, after, I should slow down here just a second. When you look up CO2, you're not going to get exactly this value. Remember, we have to look up CO2 and multiply it by 3. That's where I got this value from. So all I really do is write the reaction, look up the number, and then multiply it times the coefficient, and then write that down. Same thing for water. When you look up water's formation enthalpy, it's not going to be negative 1100. That's because I had to take and multiply that by 4. So all I'm really doing here is looking it up and multiplying it by the coefficient for every substance, and just work it right down the list. Now, once I've got those numbers, remember, it's the sum of the products. So I have to take and add those two together. That's going to give me that value. And it's also the sum of the reactants, so I have to add those two together, and that gives me that value. And then just take products minus reactants. It's much quicker, it's much cleaner, and you're much less likely to make really silly mistakes with the negative values. So this is a method I'd strongly, strongly, strongly recommend you use. Look up the numbers, multiply it by the coefficient, and write it down for every substance. Find out what the total of your products are, find out what the total reactants are, and then just take products minus reactants. It will work every time. And that finishes our Chapter 6 notes, our Chapter 5 notes over thermochemistry.